Hello, am I audible? You can confirm on the chat, please. Okay. So, good morning, everyone. Welcome to the ninth day of Deep Learning Summer School, organized by IIIT Jabalpur. And I hope you all are enjoying the learning journey so far. I am Supriya Sharma, your session chair for today. And so, for today's lecture, it's my pleasure to introduce Ms. Niharika Ahuja, who is currently working as a machine learning engineer at Google. She has previously worked at top tech companies like Microsoft and Walmart Global Tech India, contributing to impactful AI projects. She holds an MTech in computer science from IIT Kanpur and BTech from NIT Hamirpur with outstanding academic records. Alongside her professional work, she also mentors aspiring learners through platforms like TopMate, making her an inspiring figure for many of us. Ma'am, we are truly honored to have you with us today. So, without any further ado, I request you to kindly take over and begin the session. Thank you.
Hey everyone, thank you Supriya for the introduction. Um, maybe let me share my screen and
Sure,
we
ma'am.
can start. Uh, Folks, see my screen.
Yes, ma'am. Your screen is visible.
Okay, cool. So basically, like the talk for today is about transformer models. Um, and like the goal of this whole webinar is to make sure that we know what the architecture of a transformer is. And so behind transformer, there are lot of layers and lot of concepts that we are going to cover today. Um, but before even starting like to discuss about the architecture, um, I can discuss a few other things which are using transformer as a base. Um, so mostly, like the idea would be that I can take questions in the end. It's not a very, very long presentation. So once I cover everything, I can take questions. Um, so overall, like my first question to everyone is like probably everyone would have used a large language model today, right? Either Chat GPT or Gemini, Grok, Claude, like one or the other model, everyone would have used, right? And then there is like this whole area of Gen AI, which had a lot of hype starting from 2 years back, right? So the idea for Gen AI has been like a very rapidly evolving field with way too many wide variety of applications, right? So what's the concept of Gen AI? If you want to understand from a very like child perspective, so what we can say is that generative AI is basically like a child who's learning to create. So let's say you give a child a blank slate. As the child is given and exposed to more and more data, the child learns the patterns and rules of the world, and based on the patterns that it learns, now it can generate new content or new information that is consistent with those patterns. And Gen AI is very, very similar. So now, whatever major large language model you see today, right? Every every model basically uses an architecture which is called as transformer, which came in 2017. Okay. So now one important thing is to understand what the models do today. If we can understand what a transformer looks like and what a transformer does, it makes our journey easier basically. Like it makes us easier for us to understand how the large language models today are working so incredibly, right? So there was a paper, I'm not sure how many of you would have heard. Attention is All You Need by Vaswani. It came in 2017. This is a paper by Google. Uh, so this paper basically introduced this architecture called as transformer, and it completely changed the game in NLP. So whatever models existed in the field of natural language processing, transformer was a big jump. So if you see any field, right, uh, like AI is a big field to talk about, but if we talk about like specific fields, let's say computer vision, NLP, or any other field, not just related to AI, there comes a point where there has been like a major uh, revolution. And for NLP, it was this paper called Transformer, which came in 2017. The idea with Transformer was that it is built upon the attention mechanism. So basically, like whatever models existed before, this had a novel architecture. And so earlier models that existed in the field of NLP and were widely used were encoder decoder like models, which included RNN, LSTM, and so on, GRU. So there were a couple of architectures. Uh, what Transformer did was it completely replaced the recurrence which is there in those architectures with the attention mechanism to be like very specific, that is multi-headed self-attention. Okay. And don't worry about the terms. Like I'm going to cover each and everything in the upcoming slides. Okay. So the idea is that in attention, what it helps the model do is it helps the model to focus on some the most important parts of a certain sequence. Okay. And what was seen was that transformers were working like significantly, they were more powerful in comparison to the traditional NLP models, like I spoke. The idea is like when we say powerful, what does that mean? Powerful means over here for transformers that it performs also better than the traditional NLP models, and also it is much more faster as well. The reason it is faster is because transformer allows parallel processing of the input. That's the idea. Okay. So now when we say parallel processing of the input, what does that mean? When we look at the architecture, there are a couple of diagrams in the slides. It will become more and more clear as we go on in today's session. Now, apart from this, transformers have been from 2017 been a dominant architecture for most of the NLP tasks, which could include anything. So an NLP task could be machine translation, it could be text summarization, or question answering. Okay. So what does machine translation mean? I can like quickly like cover for folks who might not know. So machine translation would be, let's say I want to translate a sentence from English to Hindi, from English to French, French to English, and so on and so forth. So basically the translation task, you want a model to do that. And then text summarization, I think the term itself says what it means. So let's say you give it like a data, a text full of one page, and then you want to summarize it into like 4 sentences. So that could be an example of text summarization. Um, so now coming to how transformers really work. So there are two parts to it. In transformer, the architecture they've defined it includes an encoder and a decoder. Now, what is the responsibility of the encoder? It will process whatever input sequence you give it, and it will produce a representation of the input, which should be a good representation. Okay. Now, the decoder part. Now, what is decoder responsible for? It will take in whatever the input representation is from the encoder and try to generate the output sequence. But what it does is it generates one element at a time. So I'll give you this example. If you see in this image, just focus on the image. There are 6 encoder identical encoder layers in green, and then there are 6 decoder layers in pink. This whatever sentence this is, I don't remember which language it is, German or French, whatever it is, you give that as an input to this whole encoder layer, right? Now, what we expect is the translation of this sentence into English is I am a student. Okay. So now this architecture would not produce I am a student at once. Okay. It's not like you feed A, B, C, D in and then you get a full sentence out. That's not how these architectures work. How they work is it will produce one word or one element at a time. So it will produce I first, and then all of the like the input representation gets in along with I, and then am is produced by the decoder. And then when I and am are produced, then both of these elements will go into the decoder again, and then A will be generated by the decoder, and then I am A will go in, and then student will be produced. So whatever I spoke about right now, this is called an auto regressive model is how this works. Okay, so which basically means that the model would consume the previously generated symbols and then generate the next. Okay, are we clear till here? Is there any doubt in terms of like this slide or the previous slide? We are good. So now there comes a concept which is called as positional encodings. So in the next slide, I have the architecture of a transformer, but the idea over here is that in positional, so the architecture takes in what is called as positional encoding. The idea is that in a transformer architecture, it does not use recurrence at all. Okay. So what it means is whatever input is there in the slide, whatever you see over here, in the input, it's not like one goes in and then it uses the previous word for the next word for the input sequence. Okay. So now the model needs to know somehow what the order of the tokens is. For example, if there is a sentence which says, I am a student, versus there is a sentence which says, am a I student, right? So these two sentences are not like the second one grammatically is not correct. So somehow we need to make sure that the model actually understands the order in which the tokens are in a sequence. And if I am not making connections between the words, then how does the model really know? So, like the authors of this paper thought that what we can do is we don't have recurrence, we don't have connections in between the words in the input. So, let's use positional encodings. Somehow, so on the right hand side is the formula. So, basically, what we do is we'll have like whatever input that we have, we'll generate embeddings for it, and we'll add positional encodings which are created using this expression on the right hand side, and just add it together such that the model really knows that let's say if the sentence is I am a student, so I is on position 0, am is on position 1, A is on position 2, and student is on position 3. Okay. Now, if you see on the right hand side, basically position is where this number is, and then I is the dimension. Okay. Now, one more thing important over here is if, let's say, we use the input embedding of the size 512, whatever input that we have. If the input embedding size is 512 and we want to add a positional encoding to it, so two vectors can only be added when the dimension is the same, right? So that is why the positional encoding dimension would be the same as the input embedding dimension. Okay. Now, basically the purpose of all this is to make sure that the model is utilizing the sequence order effectively. That's the idea. Okay. So now on the right hand side, if you see, this is the architecture of the transformer. And I'll quickly cover like an overview and then we'll go in detail from layer by layer in the encoder and then in the decoder. So if you see in this image, um, I'm not sure how many of you have seen it before, but for the first time you see it, it might look complex. What happens is you send in the input, you generate, basically you can use any pre-trained input embedding also here. So let's say you have some input embedding, you add the positional encoding to it, like we've discussed already. So this sign, if you see below, is the positional encoding part. So now one more thing, the left side rectangle is the encoder and the right side rectangle is the decoder here. Now, once you add the input embedding to the positional encoding, it goes through a multi-headed self-attention layer. We've still not covered what it means. So currently you have to consider it as a black box. Now the output of the first layer goes into the feed forward neural network. The idea with this blue box which shows feed forward neural network is that whatever positions that we have, there are those number of feed forward neural networks, and for every position an exactly similar feed forward neural network is independently applied here. Okay. Basically, the idea is it just shows one box, but there are multiple, like you can imagine multiple neural networks, feed forward neural networks inside this layer. Okay. And if you see add and norm, basically, I'll cover it in the next slide. This add and norm is there around all the layers. So around the multi-headed attention layer and the feed forward layer also. Now, if you look at the right side, the overview of a decoder is that if you look at the first layer and the third layer inside the box, it's pretty similar to what the encoder looks like. So the two layers which the encoder has, the decoder also has, and then there is an additional layer in between, if you see. So this in-between layer is basically used so that the decoder can focus on the relevant parts of the input sequence. That's the idea. But now we're going to cover it in detail. So let's cover the encoder part. Okay. The idea is this is just one layer shown to you of the encoder, but 6 identical encoder layers are stacked in a transformer. It's not just one encoder and one decoder. And same goes for the decoder part. There isn't just one, there are stack of 6 identical decoder layers also. Okay. Now let's try to deep dive into each and every layer. So what we need to remember from this is there are two sublayers. One is in the encoder, one is multi-headed attention layer, and the second is feed forward layer. Okay. Feed forward is basically position-wise fully connected feed forward network. Now this add and norm box that you see, this is basically like a residual connection around each of the sublayers. Okay. The idea, okay, just one question in between. Does anyone have an idea like what does a residual connection really do? Yes, also might work. Okay, no problem. I was just trying to see if anyone has an idea. So what a residual connection does is, basically if you see the connection, right? So, and you just see this formula, layer norm x plus sublayer of x. Okay. Sublayer of x, you can replace it with whatever output that you get from the multi-headed attention layer. So basically, whatever is the input to the multi-headed attention layer, the same input x you are adding after the output that you get also from the sublayer. Okay. The idea for residual connection is that in a deep network, right? Since we are saying over here that in encoder there are 2 layers and then we are stacking like 6 encoders, right? So this is a deep network and there are chances that the model can forget information. So the whole purpose and the whole idea and the whole concept of residual connection is that it prevents the network from forgetting information, and that is why we keep adding this original input to the output of a certain layer. Okay. Now, another thing is regarding the dimensions part. I think you can relate it to the previous thing also. Let's say the input embedding dimension is 512. We discussed that the positional encoding dimension should also be 512 so that we can add it. Now that we see that there are residual connections in the network, you know that the embedding size, what you would need to add to X, right? Now should also be the same. So if X size is 512, then the sublayer of X, whatever output that you're getting from the multi-headed attention layer should also be the same, right? So it basically means here that all the vectors and all the embedding size and the output of the layers should be the same so that you can add all of this up. Okay. Now, coming to the decoder part. Over here, if you see again, I've already mentioned that it's a stack of 6 identical layers. Now, let's start with the first layer. So, there are 3 layers. Number one, masked multi-head attention. Second, another multi-head attention. And third, feed forward. Okay. So, now let's talk about the first one, which is masked multi-head attention layer. So if you see the whole difference that you see on the left side in the encoder first layer and the decoder first layer is only one thing, which is the word masked. Everything else is the same. So now it's important to understand what does masked here means and why is it masked and why not, just like multi-head attention. So why did the authors think that let's mask something in the layer? So the idea over here is that, like we said, the output generation is one element at a time. So what we would want is, like in the training data, what we would have is some, let's say it's German to English translation. So you have some German sentence with you and the translation of it is I am a student. Okay. So what we would want is when the model sees and generates I, it should ideally not look at, like it should not give attention to the words am a student. Basically what we want is that when the predictions happen for position I, they should only depend on the known inputs at positions less than I, and it should basically prevent the decoder to look and attend to positions which are in the subsequent um, on the subsequent side, right? On the right hand side. So if we are looking at I am a student and we've produced I and am, then to produce the word A, the decoder should only look at I and am and should not look at A and student, right? Because like you want to produce a certain word, why would you want to give it access to all the words which should be produced next? Okay, so that's the overall idea here, and that is where masking comes in, that you mask the words on the right side based on the position that you're looking at. Okay, now comes the second layer, which is multi-head attention. Now the main idea for this multi-head attention layer is such that the decoder can focus on, if you see like what is the input, if you like, I'm not sure if it is like very clear or the image is very, if the image is small, but the idea is that the output from the encoder layer is basically going in this middle layer, in the multi-head attention middle layer of the decoder. So what it tries to do is, it tries that the decoder can basically focus on the relevant parts of this input sequence, what it should focus on when it tries to produce I, what is the exact thing it should focus on from the input. So that's the overall idea here. So we have like covered the overall architecture part. We are now going to cover what is attention and then what is multi-headed attention. But I can stop for a minute in between if anyone like has a doubt so far. Okay, I think either everyone is understanding it or maybe you can go over it after the call also once, since the concept might be new. Uh, okay, so coming to the concept of attention, uh, like I've covered like one or two lines in brief before. The idea is that attention would allow a model to concentrate on the most important parts of the input. Okay. So similar to how humans read or human grasps concepts. The idea is, let's say if I give you a paragraph today to understand, what happens is humans also would pay attention to some specific things in the paragraph to understand what it means. Okay. So what attention also does is it mimics how humans operate or how humans try to understand a sentence or a concept. So, which is the most interesting part about all of this and about all this architecture? Because if you see, even in this image, there are so many places where multi headed attention is written, and that is where the magic is coming from. Okay. So, the idea is that it will help, like, the idea is that attention would help us learn long range dependencies. What does long range dependency is mean is, let's say you have a very large sentence and in grammar or in a language, one word is connected to another word which might be very far apart in the text. Okay. So before this architecture came in, the other models struggled to a certain extent to learn long range dependencies, which the attention mechanism kind of took. The reason like attention mechanism kind of took over is because it is able to handle this part. And now, since the model, because of attention, is able to understand how one word is important for another word in a sentence, which could be very, very far apart also, that is where it becomes very crucial to understand and grasp meaning in language. And what that led to was, now that it knows the relevant information, it knows the connections. This ultimately led to very accurate predictions.
Excuse me, ma'am.
Yeah.
Uh, Sorry to interrupt you, but could you please check some direct messages? Students are sending you doubts via direct message in the chat.
Is it? Okay. Um, let me just um, let me just pick. Um, LLM and transformers means the same. So, how an LLM is trained is another story, but the architecture behind an LLM, okay, is a transformer. That's the definition. What is a pre-trained input embedding mean? Please tell some example. So, what does pre-training also mean would come in the end of the slides. Okay. So I can cover this part then. And mm, if future words are still to be produced, then why to mask them? decoder doesn't have access to them because they are yet to be produced. So the input training data would have the whole input sequence, the whole output sequence, right? So when you send it to the encoder and decoder, you send the entire sentence. So that is why you need to mask it. So decoder does have the access to the entire sentence. Why are there two inputs from the... There are two inputs from the encoder into the decoder second layer. Shouldn't there be only one context vector input? So when we come to the attention formula and how multi-headed attention layer works, that is when you'll understand why are there two inputs. So it requires three inputs in total. So let me go back to the slide once. If you see in any multi-headed attention layer, there are three layers, right? So if you see in any one of them, like maybe see in all of them, aren't there three inputs in all of them? So you need three inputs for attention. Now for the in-between layer for the decoder, there are two coming from the encoder. That's the difference. Okay, but it needs three inputs. Now, since we haven't covered the formula, so once we cover the formula, you'll know why three in total. Okay. That cover. Okay, we are not allowed to unmute. Okay, I'm sorry, I wasn't aware. Keeps on the connections intact. They allow the output to bypass one or more to be added directly. Okay, yeah, people did answer for skip connections. So I think that looks good. And in terms of like, I'm not going to cover, let me go back. I'm not going to cover the part why is there a certain positional encoding used. So the idea would be that if you go and look in the paper, right, there are a couple of options that authors suggested that they could potentially use for positional encodings, and they did experiment with the architecture. And what they saw was that it was easier and faster to use sinusoidal embeddings there. So that's like a short answer. But if you would need more details, then I think the paper talks about, like, there's one paragraph in the paper that talks about it. Okay. So let me come to the attention part. Okay, so we've covered the brief of what attention would potentially do, right? Now let's cover the mathematics part behind it. And that is where it will be answered. Why are there two inputs coming from the encoder and why there are total three inputs in any multi-headed attention layer is what we were seeing, right? So the idea here is that there are three inputs called as Q, K, V. Q is query, K is key, V is value. The idea is Q is basically whatever vector you are currently focusing on, and then a key value pair corresponding, okay, to the input. Now, the idea is that in attention, what we do, we see and calculate a compatibility function, which is the dot product. So if you see QK transpose is the dot product or the compatibility function, which tells how much the query is matching each key. Okay. Now, to calculate a score, what we do is put a softmax over it. Okay. So after we do the softmax, we get some weights corresponding to each value, and then we multiply it with V, which gives us a weighted sum. So the idea is this compatibility function, putting a softmax over it would give us some weights, and then we know that we can multiply each value with the corresponding weight of it, which would basically ultimately tell us how much relevant those values are for the query. So that's the overall idea. Now, one extra thing, if you see over here, is dividing it by square root of dk. which is like a certain dimension that it is divided with, like the square root of the dimension is what they do. Okay. So now, like, any guesses, like, why is it divided by the square root of a dimension here? There are any answers? Sorry, I missed that before. To scale it down. Why do we need to scale it down is the question. Normalize, exploding gradient to normalize to ensure they all add to 1. There, and why would there be exploding gradient? Um, so the idea is that if the so that is right, if the q and k values are big, right? So the idea is that this value can become qk transpose. When we multiply it, it can become very, very big, right? And that is where problem could occur, because, for example, let's talk about simple sigmoid, right? So softmax works in a similar way. So if you remember, in sigmoid, it's like an S-shaped curve, right? And if the values are very, very big and you take the gradient of it, the gradient for either very big values, be it positive, be it negative, like very small or very big values, the gradient becomes closer to 0, right? So anytime we would not want, if we are passing anything to softmax, the value to become very, very big, and there is a chance that it could actually potentially become big. And that is why we normalize it, dividing it by the square root of dk. And this is also with experimentation, they came up with this exact term in the paper. Okay. So now this is just like the same representation, that Q and K and then V are all matrices. So after we do this, for each of the query, we'll get a value of Z. So this is just a representation in the matrix form, nothing fancy here. Now coming to the next part, which is multi-headed attention. So till now, we've discussed the concept of attention, how to calculate it. But in the architecture diagram, what we've seen is continuously everywhere it was written that it is multi-headed attention. So we know the term attention, then what does multi-head here mean? The overall idea for multi-head is that they found out, like in the paper, the authors found out that instead of just performing one attention calculation, okay, what we can do is maybe run multiple attentions parallelly. Okay. So what it is called as, it's called attention head. Okay. So essentially what that means is, let's have, so in the paper they have like 8 attention heads. What it means is having 8 QKV triplets. Okay. Now we have different QKVs. So QKV1, QKV2, QKV3, and so on till 8. Now, parallelly, we can calculate the attention value based on the formula for all 8 of them, right? Using this scaled dot product, the formula that we've seen already. Now, once we do that, what we can do is, with the output, we can concatenate all the 8 outputs, or whatever number of attention heads that we have. We can concatenate it together and then multiply it by a certain weight, like project it somewhere and get the final output. So now this is like, instead of just using one attention, we are using multiple attention heads with multiple QKV projections. And what they say is that overall it helps to have like lesser overfitting and it is more robust. and it generalizes better. And the reason being that those QKV triplets that we have would focus on like different subspaces, and the model would learn maybe more effectively and would have like richer representations instead of the model being completely dominated by a single type of attention pattern. So they've compared it like using one attention versus eight and maybe even more. And then they realize that eight attention heads is working pretty well. So that is where this is coming from. So now I think this is like, and some of the images in these slides are coming from this link I've already tagged here. So this is an article by one guy, and they've used these diagrams, which are very, very good to understand. So now if my input is, let's say my input sentence is thinking machines. Okay. So now one option is, there was one question, right? That what is pre-trained input embedding? Let's say we don't have pre-trained input embedding. Imagine you just initialize an embedding of size 512. So, and just randomly initialize it, seeing that if it works. So this X in green basically shows those embeddings. The 0th row is for thinking. The first row is for machines. Okay. So now that we have this, now let's say we have 8 attention heads. So what we do is, how do we get QKV? We have some W's. Having means just initialize it randomly. Okay. So W0Q, W0K, and W0V, and so on for all the 8 attention heads. Now the idea is, once we, let's say, randomly initialize and we have these W's with us for QKV, we'll multiply X with W0Q to get Q0. We multiply X with W0K to get K0, and then we multiply X with W0V to get V0. Similarly, we do it for the first attention head, then we do it for the second, then we do it for the third till the 7th attention head, right? So then we reach step number 4. So what we get is Q0, K0, V0, Q1, K1, V1, and so on till Q7, K7, V7, right? Now we know how to calculate attention. We've seen it already. So what we'll do is softmax of Q0, K0 transpose divided by, like, basically the normalization part, multiplying it by V0. So now we calculate the attention values using these QKV matrices, and we get Z0, Z1 till Z7. Okay, these are the output of the attention layers. Now the next step is to concatenate all these Z matrices and multiply it by this weight matrix, which is WO, which was there in this formula also that you see. Okay. So now that we get WO, we multiply these and we get a Z, which would correspond to basically thinking machines. And this is the whole like flow of how a multi-headed attention layer, like how does that small box in the architecture really works. Does this make sense? Let me check if there are any messages. Attention heads are within one multi-headed attention of each encoder and decoder. Correct. So now instead of 8, there could be even more, but the paper experimented that using 8, it works better. 512 embedding means 512 is the size of the embedding. So the vector size. So for example, if you see in this image, right, this X, there are 2 rows and 4 columns if you see in X. So if 4 are the number of columns, it would mean that my embedding size is 4. But this is just for representation. In the paper, they've taken 512 embedding size. Does that clear your question or not? Just maybe write a yes if you're clear on what it means. What is R here? Uh, Ignore the R for now. Other. Where did this WO come from? Okay. So WO is also initialized randomly the way this W0Q, W0K, W0V is initialized, right? And as the model learns, it would learn what the exact values of WO also should be. Okay. So all the weights are randomly initialized. These are what are getting learned from the model, no? These are the parameters of the model, which have to be learned. Uh, so only number of columns we will choose for embedding scheme, like here it's 4. In the image it's 4, but usually it is like a bigger number, and then there's a lot of experimentation whether, let's say, 256 size works or 512 works or maybe 1024 works. So it depends, but in the image how it's shown is the number of rows would be the number of input tokens that you have, and the number of columns would be the number of features or the embedding size. So basically, if the input, let's say it's a sentence, the input is a sentence, I am a student. Okay. So our input X should have 4 rows, and if 512 is the embedding size, so then this X matrix size should be 4 cross 512. Make sense? Okay. Ignore the R part. I think that's not important in the picture. Okay. To the self-attention part now. So what we've covered so far is transformer architecture, how encoder looks like, how decoder looks like, what is the concept of attention, the formula, the what is multi-headed attention layer. Now what we've said initially is the whole concept of transformer relies a lot on self attention. What does self attention mean? The idea over here is, let's look at an example and try to understand together. So let's say we want to translate a sentence which says the cat didn't eat the food because it was not hungry. Okay. So now if we look as a human being, if we look at the sentence and we know grammar, we know English. So if we are asked this question, that what does it in this sentence refer to? What we would say? Does it refer to the food or the cat? Okay. So it refers to the cat, right? And not the food. So since we understand how this language is written, is why we understand that it is associated with cat. But now, how do we make the model understand it? And self attention would basically allow it to associate that cat is related to it in some way. Okay. And the idea is that as the model would process each and every position in the input sequence, what does self attention do is it helps to look at all the other positions so that it get clues that which word is related to or is associated to which other words in the input sequence, which helps generate a better encoding for a certain word. Okay. So now this is a screenshot from the paper itself. So let me read out what the sentence says. It is in this spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult. And if you see EOS, pat, pat, it's basically EOS is end of the sentence. Okay. Now, if we are looking at the word making, what you'll see is the connections which are drawn, if you see over here, are the attention values within the same sentence. So the idea here is that if the connection is darker, the attention is more. So for the word making, laws, the word laws is not related a lot to it. Instead, for making 2000, since 2019, making this registration or voting process more difficult. So the words which are more important for the word making have more attention values in comparison to the other words. Like that's the overall idea, and that is what self-attention does. Now the formula for whatever was there for attention, it still remains the same for self-attention. Okay. The only difference is that whatever QKV goes in, the QKV goes in from the same input sequence. So let me just cover the steps once. What happens is whatever input sequence that we have, it is broken down into tokens. Okay. Like I have written it in a generic term words, but it is not really words, it is tokens. So some words can even be broken down into more tokens. So there's a step called tokenization. Now, once you do the tokenization, what does self-attention does is for each and every, so let's say the sentence is I am a student. So for each and every word, it will calculate a similarity score with every other word, including itself. And this would basically determine how much you should pay attention to the other words to calculate the encoding or embedding for a certain word. So what does that mean? If the sentence is I am a student, for the word I, it will calculate similarity score between I and I and A, I and am, I and A, I and student word. Okay. Now, similarly, for the word, let's say student, it would again calculate the similarity scores between I and student, am and student, A and student, and student and student. So you get basically similarity scores between each word and every other word in the sequence. That's the idea. Now, the next thing what we need to do is weighting, which is basically these similarity scores should act as weights, which would tell how, like basically the connections would tell if the weight is high, it would mean the word is relevant. For calculating the encoding for the term student, which word is the most important, and so on and so forth. And then basically after you get these weights, we can combine it with the original values. So basically weighted sum, the QK transpose, multiplying it, like doing a softmax would give us the weights, and then you multiply it by the value. And that is where we get a weighted sum basically, which would ultimately be the representation of that word. The idea is that this representation should ideally capture very complex relationships and dependencies between all words so that the model can understand the meaning of the sentence more effectively. Okay. So this image should make it like a little clear. Ignore the values here. Okay, 1, 1, 2, 14, all of these just ignore for now. The idea is, so we start with thinking. We have the embedding X1 for it, and then we have the QKV pairs for it. So Q1, Q2 for both the words, and then we have Ks and then Bs. Okay. So if we want to calculate the final output of a self-attention layer for the word thinking, what we would do is we are focusing on the word thinking. So we will do multiply Q with K1 and then Q1 with K2 also. We get a score from here. This is the similarity score. So thinking and thinking, thinking and machines. So let's say the score came out to be 112 and 96. This is randomly written, okay? So it depends on the exact values once, like we have a network. So once we get the scores, we divide it by 8 here. So under root of dimension K was coming out to be 8. If that is the case, you multiply, like divide it by 8. Then you take the softmax. So the softmax would give you 0.88 and 0.12. Then we multiply it with the values and then sum it up. So basically 0.88 times V1 plus 0.12 times V2, and what we get is Z1. This is the output of the self-attention layer. Okay. And similarly, we'll do it for machines as well. So for machines, we have Q2. So we'll multiply Q2 with K1, Q2 with K2, and do the same thing. Like get the scores, normalize it, take the softmax, multiply it by the value, get the final sum, and we'll get Z2 from there. Okay. So this is like in terms of the calculation part of how attention works. So now, okay. Now if you look, sorry for the numbering. So if we look into the architecture diagram, right, what we see is there are three types of attentions. One is encoder decoder attention, the second is self attention in encoder, and the third is self attention in decoder. Let me cover the self attention in encoder part first. So if you see in that diagram, all key query value, everything is coming from the same place. There were three inputs going in, right? The idea is that if obviously if the encoder layers are stacked up, so it would mean that it is taking the output from the previous layer of the encoder. The idea is that each position in the encoder should attend to all the positions in the previous layer of the encoder. That's the idea. Now, same goes for the decoder first layer. The only difference was it is masked multi-headed attention layer, but all the keys, values, and queries are also coming from the same place in the first layer of the decoder. And the idea over there is that we want to allow each position in the decoder to attend to all the positions in the decoder only up to that position and not beyond. The third type is encoder decoder attention, which is the middle layer in the decoder, where there are three inputs, and there was one question, right, by one student saying that why are there two inputs coming in from the encoder layer? So that those are the keys and values, two inputs coming from the output of the encoder, and the queries are coming from the previous decoder layer. So the idea over here is that it will allow every position in the decoder to attend to all the positions in the input sequence. Like, because it should have it, right? Whatever our input has to generate a certain output, let's say it has to generate the word I, which positions should it attend to in the input sequence? It should understand to even generate the word I. And this is where the concept of this encoder decoder attention, which is the middle layer in the decoder, comes into picture. Okay. So I can cover this diagram. Let it maybe finish. I can take up if there are any questions. Only keys and values are coming from the encoder. So the whole concept of attention is that it calculates values, how much it should give attention to, and the focus is the query. Okay. So if I want to generate the word A, it should focus on everything till I, so that becomes the query. And then what it should attend to comes from keys and values, is why it is coming from the encoder. Okay. Now, if you look at this image, what is happening is, like if you see step by step, it basically shows us how the output is getting generated. So the input, if you see, everything is given together. Whatever, Jesus, whatever, I cannot pronounce it properly. But once we get it on step number 1, if you see, once it generates I, it goes in, and in the next step it produces am, and now I and am is there, which goes in together and produces A. After the decoder layers, there's one linear plus softmax layer, then it takes I am a, produces student, and then I am a student goes into the decoder and it produces end of sentence. So now one thing important here is that there are markers which are used in transformers, which would tell you start of the sentence and end of the sentence. Start of the sentence is not shown here, but it is usually always there, that you send in start of the sentence and then the decoder starts producing. And because we need kind of a stopping criteria on when we know that the whole sentence, whatever the decoder had to produce, it has generated already. So basically, like end of the sentence marker acts as that stopping criteria for us, that we can stop when the decoder produces this term. Okay. Now, one more thing over here is the linear plus softmax layer, which we did not talk about. The overall idea for linear plus softmax is basically like to produce a certain word, right? We cannot just do it using an embedding. So we would need a score. Let's say our vocabulary size is, let's say, 2000. For now, it would be bigger, but let's say it's just 2K. So the idea is softmax would produce some scores across all words in your vocabulary, and then you can pick based on different criteria. But one simple criteria would be that, let's say, the probability or the value is the highest for the word I after the softmax layer, so you know that the output is I, like you're picking I from there. Okay, so that's the overall idea. uh, so it was seen in this paper that there are some different models which were there before, and it compared it with them, and it was seen that it performs either like on English to French and English to German translation. This is the very first paper, so it was seen that it performs better in comparison to the other models. Okay. Are there any questions? Okay. Let's come to like the last part of the talk today. A very small part, maybe I can take questions in the end only now, since there isn't much remaining. So, like the way NLP model training has evolved over time, there are two things which have emerged primarily in the last few years, which includes one is the rise of pre-train and fine-tune. The idea here is, and I think this is the term I used before, like a pre-trained embedding. So this is what I was referring to, that there is a slide which would come up. The idea is that before, like a couple of years, how NLP models were trained were solely relying on label data. Okay. That I'll give you an example. So let's say if we want to do machine translation, let's say we want to do English to Hindi translation. So we need a lot of training data for the models to really understand. Let's say the sentence is, I am a student, the Hindi would be, मैं छात्र हूँ and whatever, right? So a lot of training data we need for it. From that, what we've moved towards is pre-train and fine-tune approach. The idea is, what does pre-training, what's the word pre-training mean? An example of it is, let's say you give unlabeled text. Let's say there's a vast library and there are so many books that you have in your library, and you give your model everything, okay, to grasp language fundamentals from it. After it, what we get is a pre-trained model. Okay, this data or this text is not labeled, which is an important part in pre-training. Okay, so like in general sense, like the models that we have today, they are pre-trained on a lot of like URLs which are there on the web. For example, all the Wikipedia articles, all the news articles, and so on and so forth. It depends on what you want to pre-train it on. But the idea is that you feed a lot of unlabeled text so that it grasps how a language works and feeds in good amount of information. Okay. Now, what is the fine tuning step? Now, let's say we have now a pre-trained model with us. So in fine tuning, we would just need a smaller set of labeled examples so that the model can excel at a specific task. So let's say if we wanted to do machine translation before, we might need 500K examples to teach the model how to translate. But now, let's say, even if we have, let's say, 10K examples instead of 500K, and we have a good pre trained model with us, it could help excel at the task, which is the fine tuning part, where we'll have just a smaller set of labeled examples, which is very similar to like a student wants to specialize in a certain thing. So a student gets some smaller information out of which the student is able to excel at that task. Okay. It could be answering questions, it could be translation, it could be anything. Okay, any task for that matter. This is the first paradigm. The second paradigm is the emergence of pre-trained, prompt, and predict. So the pre-training part remains the same, but instead of even fine-tuning, what has been what is being used today a lot, apart from fine-tuning concept, is the concept of just prompting. I think which everyone might have even used. So the idea for prompting is that you have a pre-trained model which has a lot of existing knowledge. What we do is we give the model a prompt and it uses that to help us do the task that we want to do. So for example, if you want to do a translation, and if you want to translate, I missed the bus today into French. So a prompt could be saying the English colon, this is the sentence, and then French colon. And the model would essentially use the knowledge that it has about both the languages and then complete the sentence. So this is the overall idea. Now, like this is not in the scope of this call, but prompting also has different ways. This is just one single way I've written, like English colon this, French this. There are different type of prompting methods. If the pre-trained model is not performing well just with this, right? There is an option that you can give it few shots. What does few shots mean? You give it some examples on what you expect the model to do, and based on that and its pre-existing knowledge, it and then you can evaluate how good it is performing. Okay, so this is an old image which is basically telling about the architecture in large language models. So the base is of a transformer. Given this is an old image, this talks about from 2018 to 2023. Okay. But the idea is one type of architecture in a large language model is that you just use the encoder out of this whole encoder decoder model. Okay. So if you're just using the encoder, the example of various models are BERT, Robota, DistilBERT, BioBERT, and so on. So this is a whole series which came in, which used only encoder only models. And then if you just use the decoder, okay, part of this architecture, then these are called as decoder only models. An example of it is the whole GPT series. There is the Gemini series, let's say Gemini 2.5, 2.0, Pro, Flash, whatever. Okay, Llama, Lambda, etc. These are decoder only models if you just use that part from the architecture. And then there are models which use both encoder, decoder, which include some models like which are BART, T5, T0, FLAN T5, etc. So I have also tagged the survey paper on LLMs here, where this image is taken from. So this is a good now that from this call everyone would have like a at least a basic decent idea of what the architecture and of a transformer is, and some idea of LLMs from this. So maybe if you go ahead and like go through this paper, this would give you more insights on other things which have not been covered in this call. Okay. Yeah, I think that's all I have. And I can take up questions now. Uh, and I've like added my LinkedIn. Feel free to connect with me on LinkedIn. I'm usually pretty active there. So yeah, thank you. Let me take up questions. So, so there are different type of training methods. If you just use the encoder or you just use the decoder part. Okay. So the idea is that if you, let's say, are using just the decoder only part, right? So then there's no connection which is coming from the encoder only part, right? That in between layer, you don't have the encoder output at all. Why only encoder and only decoder models are used? So basically, see, the idea is that I'm not sure if you would have heard, in a lot of places, you need very good embeddings of inputs. Okay. That is where encoder only models come in. So if you don't even use the decoder and train your model on only the encoder part, okay, what you'll generate is embeddings, and those embeddings. So BERT is one model which is very, very famous for generating and having like very good embeddings of text. Okay, that is where encoder only models come in. And then decoder only models are good when you want to generate the text. Taking I generate am, taking I am generate a, taking I am a generate student. So when I talk like one thing I mentioned was um, that for models like Gemini or GPT, they are using decoder only models, right? The reason it is using decoder only models is because it's a generation task, right? That I put in Gemini, what is the weather today? And it's generating some text. So it needs that particular uh, generative capability, right? Which the decoder is giving us. So that is where it is coming from. Okay. Um, hands-on. Hands-on part, it would be clear in the afternoon. Machine translation task. Like transformers are trained on for textual data. Do we also have such models for videos? Can we train a model for any audio or video data and generate such stuff? Yes. The short answer is yes. Uh, okay. Maybe I'll completely answer that later, Juhi. But has anyone seen the demo in Google I/O for VO3? Then maybe so VO3 is the first model which has like a video generation capability along with audio. Um, kind of had a lot of buzz with that model in the market. So you should definitely look at that. So yeah, basically the architecture of this transformer remains the same. The mode it started with is text, but today it is being used for videos, images, audio, everything. Okay. Now, how it is processed completely changes. So, what happens is, for example, for images or videos, right? Um, I'll not like do a deep dive, just giving you a one liner overview on it. So, let's say you want to train a model somehow on videos, right? Or images, and the input structure still remains the same. Your X looks like an embedding, right? So number of tokens times the embedding size is what our X looked like in Transformer. So we need to somehow make that X, be it images, be it videos, or whatever. So, for example, if it is images, what we could potentially do is, let's say the image, whatever the image size is, you can flatten it and then generate an embedding out of it. And once you have an image embedding, the same way you can put an input for it. So the overall structure, architecture, everything remains the same. The way you have to process it would probably change. So there are different image embedding or video embedding models which exist. So we could potentially use those ideas and get our input to this architecture. That's the idea. Computations for text versus images and then videos. For videos is definitely huge. There are like a lot of tricks which are used how to process videos. Like, for example, like one way is whatever video there is, whatever audio it has in it, you transcribe it, and then you have text again from that video. So, what to generate next? So, it's like video is a complex thing because it includes images plus text and then transcribing and getting the audio also. So there are like different specialized models that exist, and there are different training, like people have added different tricks and different training methodologies also to this. And even for LLMs, like even for like text-based models, there are different ways to train it. People have been experimenting with it a lot in the last 2 years. Anything else? Let me stop sharing. Yeah. Have other models. No, the architecture of a transformer model is this. There's no other architecture. The way it is trained has different methodologies. So that's an advanced topic. So there's a concept called, like, for example, I covered the fine tuning part, but not in detail. So there is this supervised fine tuning. And the second thing is RLHF, then there is DPO. So there are some techniques which are used, but in terms of the architecture, this is the architecture that we have for text. Now, how image transformers work or how videos work, that is not being covered in this. Um, for a minute. Are built on top of RNN or replace the RNN. This replaces the RNN. See, the architecture in RNN is that there is a hidden layer, and each node in these series, everything is connected. Okay. So there's a recurrence in RNN. So this architecture completely replaces RNN or LSTM or GRU. That's the idea. in terms of textual data. Why could time series signals not being, why do you think that time series could not be processed? It might not work very well with transformers. That's another thing. See, you could, whatever sequence models exist, right? Based on the problem that you're trying to solve for, the idea is you try to use RNN, LSTM, GRU, or um, transformers and see which one performs the best. For ECG signals also, what would you send in? You can somehow create, if you can create embeddings and pass into the model, then you could use a transformer also, and then you could use an RNN also there. So it depends on what is performing better for you in terms of what the problem that you're trying to solve for. In general, it is seen that transformers can process time series, but the forecasting, like how good they are, is a question. Any other question? Anyone else has a question? Yeah, I hope it was helpful. Um, and yeah, if anyone has a question and feel like wants to connect, I can speak with you on LinkedIn. Feel free to like reach out to me there. Um, that works.
So should we wrap up now, ma'am? Thank you so much, ma'am, for sharing your valuable knowledge with us. It was truly a great session. We deeply appreciate your time. Thank you so much.
Bye bye.
Thank you, ma'am.